As of now, we know that how actually the precipitation happens. So far, so good. But we'll be extending our knowledge by what's the effect and how do cloud droplets actually grow larger and what types of effect actually works behind this. So we know so far that cloud droplet form around the condensation nuclei, and we have talked about two types of condensation nuclei. That's one is hydrophobic and hygroscopic. So hygroscopic, that water seeking, salt, dust, volcanic ashes, very tiny portion, very tiny um, dust. So just imagine now that an ordinary cloud droplet is extremely small. So having an average diameter of 20 millimicro like micrometers. So the typical cloud droplet is more than 100 times of that very tiny 20 micrometer droplets. If a cloud droplet is in equilibrium, which means that the surroundings, the size of droplet does not change because the water molecule condensing onto the droplet will be exactly balanced by those molecule evaporating from it. So it is equilibrium situation. Consider a situation right now. A cloud droplet is in equilibrium with its environment. The total number of vapor molecule around the droplet remain fairly constant and defined the droplet saturation vapor pressure. That vapor pressure, we called it the droplet's saturation vapor pressure. Okay, since the droplet is in equilibrium situation, the saturation vapor pressure, we will be calling it equilibrium vapor pressure. So if you are looking over the picture here, the curvature effect, you will understand that the rounded water droplet has curvature, when the standstill head has the less curvature. Let's move forward. To keep the droplet is in equilibrium, again, the more vapor molecule are needed around it to replace those molecules that are constantly evaporating from its surface. Smaller cloud droplets exhibit a greater curvature relative to the size of a water molecule. So it causing a more rapid rate of evaporation. As a result of this process, we would call it curvature effect. The smaller droplets requires an even greater vapor pressure to keep them from evaporating away. So as the droplet is small, the curvature effect will be greater. So therefore, we can say when air is saturated with respect to the flat surface. So this flat surface means maybe it's an ocean, it's a pond, it's a lake. So when the air is saturated with respect to a flat surface, it is unsaturated with the respect to a curved droplet of a pure water. So when we are talking that in the ocean or a lake, the water is saturated, water is equilibrium situation, but the same temperature or same situation, this tiny water droplet would not be saturated, would be somewhat unsaturated. That's the main point here. So to keep tiny cloud droplets in equilibrium with the surrounding air, the air must be supersaturated if we'd like to keep that in equilibrium situation. So the relative humidity must be then greater than 100%. The smaller droplet would give us the greater its curvature relative to the size of the water molecule, and the higher the supersaturation will needed to keep the droplet into the equilibrium situation. So if we look over the graph, the drop in equilibrium is a red color. If you look very carefully, the droplet of the diameter, if that is reduced, so equilibrium situation, we need more relative humidity to make that situation equilibrium. If you are looking at this graph, you can understand. Just as relative humidity less than that required for equilibrium, a water droplet to evaporate and shrink, those greater than equilibrium value allows the droplet to grow by condensation. Okay, now let's talk condensation nuclei. We know that two types of condensation nuclei. One is hygroscopic, one is hydrophobic. Again, because of many of the nuclei are hygroscopic, that they have an affinity or affiliation for the water vapor, the condensation may begin on such particle when the relative humidity is well below 100%. So when we have a hygroscopic condensation nuclei around us, even though the relative humidity is not right now 100%, the condensation may occur around that hygroscopic nuclei. When the condensation begins on hygroscopic salt particle, for example, if they dissolve forming a solution, become the salt ion in the solution, bind closely with water molecule, it is more difficult for the water molecule to evaporate because the hygroscopic condensation nuclei attracting the water vapor, the water molecule. So this condition reduces the equilibrium vapor pressure, and this effect we call it solute effect. So here we have two types of effect. One is solute effect, one is curvature effect. Solute effect actually preventing us for the evaporation. Curvature effect actually accelerating our evaporation process. Solute effect is keeping to the equilibrium situation. Curvature effect actually making evaporation faster. Okay, as the droplets grow larger, the solution become more dilute. We know that. Imagine, for example, that we place a cloud condensation nuclei of different sizes into moist but unsaturated air. As the air cools, the relative humidity increases. When the relative humidity reaches a value nearly 78%, for example, condensation may occur on the majority of nuclei. As the air cools further, the relative humidity increases, with the droplet containing the most salt reaching the larger size. And since the smaller nuclei are more affected by the curvature effect, only the larger nuclei are able to become cloud droplet. So the real world, over the landmass, where large concentration of nuclei exist, there may be many hundreds of thousands of droplets per cubic centimeter, all competing for the available supply of water vapor to make that condensation nuclei or droplet bigger. Over the ocean, on the other hand, where condensation nuclei are in a small number compared to the land, there are normally fewer, typically less than 100 per cubic centimeter, but larger cloud droplet. So, in a given volume, if we compare, we tend to find more cloud droplets in the cloud than over the land. But on the other hand, the less cloud droplet, but bigger in size over the ocean. So those all are the situation for cloud droplets grow larger, and we know the two effect. One is solute effect, another one is curvature effect. So solute effect actually giving us like not having cloud droplet growing larger, but curvature effect actually, solute effect actually helping us to grow the droplet bigger, but curvature effect actually enhance the evaporation. So those are the opposite effect. So I think the inside mechanism of the precipitation process means cloud droplet growing mechanism, we have an understanding about that. Thank you. We'll be talking about now. The next is the ice crystal process.